We're looking at notes for 6.3, homogeneous differential equations. So let me just read through the notes here. Differential equations need to be separable in order for us to use available integral rules to solve. So note that not all differential equations are separable. So for instance, here, now no matter how we divide, multiply, subtract, add, we're not able to nicely separate the dy and y's on one side and x and dx on the other side. So for differential equations that are not separable, we can use slope fields to graph potential solutions, even though integral rules are insufficient to solve. Some differential equations that are initially not separable can be made to be separable through the use of change of variables. That is true for differential equations in the form of y prime is equal to f of xy, where f is a homogeneous function. So the function is given by f of xy. It's homogeneous of degree n if we're able to factor out t from the function where n is a real number. So what we're going to do, let me just go through the steps here. Determine if the function is homogeneous. We're going to take the equation and we're going to replace t x for each of the x's we see and ty for each of the y's that we see. So, and then we're going to work to simplify the equation and attempt to factor out factors of t and rewrite it as t to the nth degree times f of xy. So if t to the n can be factored out, then the function is homogeneous with a degree of n. So example 1, determine the function is homogeneous. If so, determine the degree. So we have f of xy being x squared plus y squared. So first step, we're going to replace every x and y we see with tx and ty. So the x squared gets replaced with tx quantity squared, y squared gets replaced with ty quantity squared. Now if we look at this expression here, if we distribute the exponents through, we get t squared x squared plus t squared y squared. We're able to factor out t squared out cleanly, x squared plus y squared. So we're able to factor out t to the second power and not have any t's left over. So we therefore can say f of xy is a homogeneous function of degree 2, since we're able to factor out a degree of 2. Example 2, we have f of xy being x squared y minus 4x cubed plus 3xy cubed plus 1. So we're going to determine if this is a homogeneous equation. So replace every x and y with tx and ty. So x squared gets replaced with tx quantity squared times y gets replaced with ty. 4x cubed, so x gets replaced with tx quantity cubed. Here the x gets replaced with tx, y gets replaced with ty quantity cubed, and then plus 1. The plus 1 has no variable to replace, so we leave that one alone. Now if we simplify this or expand this out here, t squared x squared times t times y, so we have t cubed x squared times y, so t squared times t gives us t cubed. For t cubed x cubed, we're able to take out t cubed. Here we're able to do t times t cubed, which is t to the fourth rather. So that should be 4. T to the fourth times 3xy cubed. Now notice that we're not able to factor out the same powers of t for each of the terms. So since we're not able to do that, since we can take 3 from these terms, we can take 4 from here, we can take none from here. So f of xy is therefore not a homogeneous equation or a homogeneous function. Okay, example 3, f of xy is x squared plus y squared over square root of x squared plus y squared. So we replace every x we see with tx, replace every y we see with ty. So x becomes tx quantity squared, y becomes ty quantity squared, square root of tx quantity squared plus ty quantity squared. If we clean this up, we get t squared x squared plus t squared y squared. We can factor out a t squared. Here we can also factor out a t squared. Now notice that if I take the square root of t squared, it comes out as just t. So we get t squared over t, which is just t to the first power, times x squared was y squared, square root of x squared plus y squared. So we're able to factor out t cleanly, and we only factor out t to the first power, so therefore f of xy is a homogeneous function of degree 1. The degree is based off of the exponent for the t. Let's go to the back here. Steps for solving homogeneous differential equation. So first thing we do is we verify that the differential equation f of xy is homogeneous and determine the degree n. Second, we multiply the numerator and denominator by the differential equation by 1 over x to the nth. Okay, we substitute all our y over x with variable v, so we have v as a placeholder here. Through the change of variable, we solve for y, so that y is equal to vx. We then find the dy over dx using product rule, so product and chain rule here. So y becomes dy dx. V and x, we have to go through product and product rule and implicit differentiation. So v becomes, so f prime g plus f g prime, so v becomes dv dx times x plus f times g prime, so x becomes 1, so then we have dy over dx equals dv over dx times x plus v. Replace dy dx in the differential equation with the above expression, and then we try and solve the resulting differential equation by separating the variables, so v and dv on the left side and x and dx on the right side, and then we go through our integral rules to see if we can find the integral of both sides, and then finally replace v back in terms of y and x, and then solve for y. So example 1 here, if I replace every x and y with tx and ty and every x with tx, if I go through that procedure, I can factor out t to the first power, so we know this is going to be a degree of 1. Okay, so degree of 1. Next step, we're going to multiply the numerator and denominator differential equation by 1 over x to the n, and we know degree 1, so 1 over x to the first power. So we take the x plus y multiplied by 1 over x to the 2x, the same thing, multiplied by 1 over x. Distribute through, we get 1 plus y over x, and then the x's cancel out for the bottom. So we have 1 plus 1 over x, y over x over 2. Now, next step, we're going to replace y over x with v. So replace this with v. So we get 1 plus v over 2. We know that since v is equal to y over x, we can go through the procedure, solve for y, and then we go through implicit and product rule. We get dy dx is equal to dv dx times x plus v times 1, which we just talked about that with step 5. Okay, next step, we're going to replace dy dx with this expression that we just found. So here is our step here. We have dy over dx equals 1 plus v over 2. So replace dy over dx with x dv over dx plus v is equal to 1 plus v over 2. So now we can try to separate the variables. So we want the v's and dv on the left and x and dx on the right. So algebraically, let's see what we can do. We can find common denominators being 2, so 1 plus v minus 2v over 2. Combine like terms, we have 1 minus v over 2 is equal to x dv over dx. Now let's see what we can do. If I divide the 1 minus v over to the left, and if I multiply the dx over and divide the x over to the other side, we can separate the variables. So dv over 1 minus v. 1/2 stays. X gets divided over, so 1 over x, and dx gets cross multiplied on the other side, so it becomes dx. Notice my dv and dx are separated, and they are in the numerator position. So we have dv over 1 minus v is equal to integral of 1/2 1 over x dx. So now variables are separated. We just have to identify the appropriate rules for the left and the right. Looks like the left side is in the form of integral of 1 over u du, so natural log rule. And then here, this is also a natural log form. So let's see, for the left side, it takes a little bit more work since we have more than one term in the denominator. So we let the u value be 1 minus v. du over dv is -1, dv equals negative du. We make our substitutions. So dv gets replaced with du, negative du. 1 minus v gets replaced with u. And then the right side, we have 1/2 times integral of 1 over x dx. Left side here, negative natural log of absolute value of 1 minus v. That's the rule for 1 over u du. Here, same thing. 1 over x becomes natural log absolute value of x, and then plus c on the right side. So now we have to decide what we can do to clean this up and solve for v and get the v and the x to be brought out from under these natural log expressions. So first step, I'll move the -1 up as an exponent. So natural log of absolute value 1 minus v to the -1. I'll bring the 1/2 up as well as exponents. I'm going to combine this together since I can use product property. So we know Ln of A plus Ln of B is the same thing as Ln of A times B. So here, combine the x to the 1/2 and c. So now we have two natural log expressions on either side. I'm going to raise both sides with base e, which will allow me to cancel out the natural log expression. I'm just left with 1 minus v to the -1 times x to the 1/2 times c. I just pulled the c out in front. All right, so now I've found the indefinite integral, and now it's just a matter of trying to solve for x and trying to get this in terms of x and y. So we know v before is assigned as y over x, so replace v with y over x, so 1 minus y over x to the -1. Find a common denominator. I get x minus y over x to the -1. This is equal to cx to the 1/2. I can flip the numerator and denominator to get that -1 exponent to go away. So x over x minus y is equal to cx to the 1/2. Now I want to try and get rid of the x to the 1/2, so I'm going to raise both sides, square both sides here. So x quantity squared, so x over x minus y quantity squared is equal to cx to the 1/2 times quantity squared as well. So if I square the numerator and denominator, this is my expression. C squared will remain as c, since c just represents a constant. X to the 1/2 squared is cx. So now we have everything in terms of x and y, no radicals. And now it's just a matter of trying to clean this up here a little bit more. I'm going to multiply x minus y squared to the right side, and then divide the x over to simplify. So I'm left with x is equal to c parentheses x minus y quantity squared. So now we've solved this differential homogeneous equation.